Today we're going to talk about lesson 2.2, which is about inverse variation. In lesson 2.1 you learned about direct variation, so now we're going to talk about the inverse variation. In this box, definition of inverse variation function. It's a function that can be described by the formula of the form y equals k over x to the nth. K cannot equal 0 and n has to be greater than 0. So let's go through that a little bit better. For the inverse variation function with equation y equals k over x to the nth, that's that same equation I just said, we say y varies inversely as x to the nth, or y is inversely proportional to x to the nth. In an inverse variation, as either quantity increases, the other decreases. And that's the key to it. As one gets bigger, the other one is going to get smaller, and as one gets smaller, the other will get bigger. So as one increases, the other decreases. Let's see that in two examples. Example 1a, the speed s of a bike varies inversely with the number b of back tier geeth on the rear wheel. Write an equation that expresses this relationship. So speed of the bike varies inversely, so it's s equals k over b to the first power, because we know n equals 1. And that's an inverse variation function. What that tells us is, as the bike goes faster, the number of back gear teeth are going to get smaller. Or the more the number of back gear teeth we have, the bike's going to go slower. In example 1b, the number of units u in a length varies inversely with the length L of the unit. Write an equation that expresses this relationship. So we could say u equals k over L. So u varies inversely with length. Okay, let's solve some inverse variation problems. According to the law of lever, and that law of lever has to do with simple machines. If you study engineering, you'll learn about simple machines. But in that law of lever, in order to balance a seesaw, another person must sit a certain distance d from the pivot, which is called the fulcrum on a lever. It's the point that it pivots, and that's of the seesaw. This distance is inversely proportional to their weight. So that distance is inversely proportional to the weight. So d equals k divided by w. Since d is inversely proportional to w, as distance d increases, weight will decrease. This means a lighter person can balance the seesaw by sitting further or farther from the pivot, or a heavier person can balance a seesaw by sitting closer to the pivot, because d and w are inversely related to each other. So let's go through this example. You can see Ashley and Sam on a seesaw, and they're trying to balance it. Sam weighs 42 kilograms, and Ashley weighs 32 kilograms. So Sam weighs more than Ashley. So we know that as weight increases, distance must decrease, or as distance increases, weight must decrease, because they're inversely related to each other. So Sam is 2 meters from the pivot or that fulcrum. How far away must Ashley be in order to balance Sam? So we're going to solve for D. We're going to use those 4 steps that we learned in the lesson 2.1. So step 1, we're going to write our function. We're going to say D equals k over w, our general equation. Step 2, we're going to solve with what we have. So we have distance that Sam's away is 2 meters. We're going to solve for k, and his weight is 42 kilograms. So he's 42 kilograms and he's 2 meters away. So we're going to solve for k, multiply both sides by 42, and we have k equals 84. In step 3, we're going to plug in that k value. So we have d equals 84 over W using that equation we wrote from step 1. And in step 4, we're going to plug in the rest of the information we have. We're trying to solve for Ashley's distance, and we know her weight is 32 kilograms. So her distance would equal 84 divided by 32 would be 2.625 meters. She needs to sit 2.625 meters away from the pivot point in order to balance that seesaw with Sam, who weighs more than her. Okay, let's work through another problem to help you understand inverse variation. Example 2b, this time Carrie weighs 34 kilograms and is 1.8 meters from the pivot of a seesaw. If Madison weighs 38 kilograms, how far from the pivot should she sit to balance Carrie? So step 1, we need to write that general equation. So D equals distance equals K over W, because they're inversely related. Step 2, let's solve for K. We know Carrie is 1.8 meters away, so 1.8 equals K over, and Carrie weighs 34 kilograms. If we solve for K, K equals 61.2, because I multiplied 34 by 1.8. In step 3, D equals 61.2. We're going to plug in that K value into that equation from step 1. And then in step 4, we're going to solve for D because we want to know how far she needs to be away from the pivot. And we're talking about Madison now, and she weighs 38 kilograms. So D equals 61.2 divided by 38 is 1.61 meters. She needs to sit 1.61 meters away, which makes sense because she weighs more than Carrie, so Carrie gets to sit further away. She has to sit closer because she weighs more, because the weight and the distance are inversely related. So let's talk about an inverse square situation. Just as one variable can vary directly as the square of another, one variable can also vary inversely as a square of another. The next examples illustrate this, where the intensity I of light is inversely proportional to the square of the distance d from the light source. And here's that function, I equals k over d squared, and that's where that square comes in, an inverse square situation. Okay, so we said it was I equals k over d squared. So example 3a. Suppose the intensity of the light 4 meters from a light source is 40 lumens. A lumen is the amount of light that falls on a 1 square foot area, that is 1 foot from a candle. Find the constant of variation and determine the intensity of the same light 6 meters from its source. So step 1 I already did for you. That was the general equation, I equals k over d squared, which they gave you. Now step 2, we're going to solve for k. So we say I is 40 lumens, that's the intensity, equals k over, and the distance is 4 meters, so 4 squared. So let's solve for k. We got to square the 4, so we have 40 equals k over 16. K equals 40 times 16, 640. That's our k. In step 3, we're going to use our equation we wrote in step 1 and plug in our k. So I equals 640 over d squared. And then in step 4, we're going to solve for the intensity of that same light that is 6 meters from its source. So intensity equals 640 over, our distance this time is 6, and we have to square it, 6 squared. So intensity equals 640 divided by 36, because 6 squared is 36. Our intensity is 17.78 lumens. That's our intensity of the light when it's 6 meters from its source. Okay, in example 3b, suppose the intensity of light 6 meters from a light source is 30 lumens now. Find the constant of variation and determine the intensity of the same light 9 meters from its source. So in step 1, we're going to write that general equation. We can say I equals K over D squared. In step 2, we're going to solve for K. If we know the intensity is 30 lumens now, equals 30 equals K over D squared, and our distance is 6 meters, so 6 squared. So 30 equals K over 36. K equals 30 times 36, which equals 1080. That's our K value. So in step 3, we're going to use the equation from step 1 and plug in our K value. And then step 4, we're going to solve for our intensity, because they want to know the intensity of the same light 9 meters from its source this time. So intensity equals 1080 divided by 9 squared equals 1080 divided by 9 squared is 81. Our intensity equals 13.33 lumens. So the light that's 9 meters from its source, which has a light source of 30 lumens, is now going to have a light source of 13.33 lumens.